like this, and now it's on, and you can put this in a pocket or something if you like. Yeah. You don't have to clip it unless you want. You could just put it in a pocket. Up to you. It doesn't seem to interfere much with keys or.
Okay. Oh, that's a long one.
Yeah. Defend yourself.
Okay. And I just.
Oh, for advancing slides, I would say the easiest is just use your arrow key or just plug or something.
Yeah.
You don't have a clicker. Let me try to get more.
I never
The only Christian is out there. He's coming back in.
Yeah, that's great. That's great. Thank you. And thank you to the organizers for inviting me to this great workshop. I learned a lot. And I thank everyone I've been talking to who has presented interesting talks here. So it's a bit of a new field to me, so I'm learning and learning. Even this project here I'm going to talk about is sort of a new direction for me. So bear with me. Okay. This is about gauge theory, of course. I don't really have that much to say about confinement yet, perhaps later, but not in this talk. But where I'm situated in a diagram of adjoint matter gauge theories is down here, right? No, because it's just scale. This is the number of adjoint scalars and the number of adjoint fermions. N equals 4, super Yang-Mills is here in the middle. It's a beautiful theory, although it's perhaps not what we are most interested in here today in this workshop. But to learn about these theories and what properties they have is sort of a general question. And there are some interesting relationships here which are a bit surprising. Now, focusing on this part will get us into the problem of not just looking at the couplings of the gauge couplings, but also scalar couplings, interactions of scalars. What can that do to the properties of the theories? So why do I want to look at this? No fermions. It's actually started, well, it started with an attempt to do holography, but then I found a curious old question about just Yang-Mills and bostonic strings, which was apparently sort of left hanging. There was no, and maybe reasons for that. Why would you worry about bostonic strings at all and the relation to Yang-Mills? It is curious though, and I had the tools to look at it, so I started looking at it. Now, in the process, we rediscovered, I should say this work is together with an excellent grad student. we discovered a way of doing the calculation. Just it was just a tool for us in the beginning, but it was an algebra that has strange properties, and it seemed to be surprisingly powerful to us. And I will talk about that. That may be more of more interest than the particular model can be generalized. It was a rediscovery when we put the preprint on the archive. I got a mail from Hugh Osborne, so who recognized this algebra, and some of you may also recognize it. But I'll come to that later on. It hasn't been overused, I should say. Maybe there's a reason for that. For the moment, I think there is no reason to not use. You should really look at this algebra. It seems to have interesting properties, but the jury is still out. Okay, what was this curious issue about scalar adjoint gauge theory? Looking at the beta function, say we have m adjoint scalars. The beta functions for Yang-Mills coupling takes that form. I'm written it in a large N format because many of the things I do will be simpler and more natural in large N. This relation, of course, doesn't make much of a difference. What's curious about this is that 22 adjoint scalars is, you get that from dimensional reduction of bosonic, just ordinary Yang-Mills in 26 dimensions. Of course, you don't really think that's a theory in 26 dimensions, but formally you could ask, what is this? Why would you start and get something at least on one loop level conformally invariant, the zero beta function? Why would you get that?
To make it 26.
To make it
26.
yeah, yeah. I mean, you get, yeah, you get it right. That's and then why is this? I mean, that's as Igor says, it has this kind of theory has a sort of interpretation of it as a low energy limit of a bosonic D brane. But this is nothing you would think about if you were just looking at it from a gauge theory perspective. It's a bit of a mystery from that perspective. And why would the gauge theory know about the critical dimension, which is of course 26 of a bosonic string? Why would it know about it, really? No, I mean, that's the significance of one loop is just that it's the first result that is independent of the interactions. Of course, there are corrections. There are, of course, the theory in bosonic string theory is not a well-behaved theory either. So you have to have corrections, there are tachyons, etc. So your point is, of course, valid. This is an observation. In the end, you have to some higher loop diagrams as well. But even this observation is, it's a bit curious. You could also ask if you ask certain questions in bosonic string theory, you can forget about tachyons and other thicknesses of the theory do not have any influence. Are there similar questions in Yang-Mills theory? Is there a way of taking limits, etc., that makes it a more self-contained theory. This is something that I can study, right? It's a question. I mean, there are higher loop amplitudes or higher loop corrections, of course, in beta function. But as yet, you know,
discrete. So it is an exponent that something the beta function is exactly have one parameter.
yeah, no, I mean, I agree completely. It's a curiosity. It is a curiosity. But you know, I'm curious. That's it. And there may be something here, and we don't know. I mean, I didn't. Oh, yeah. Yeah. I mean, okay. There is a quartic interaction. It's this commutator squared thing. If you just take the classical action for the, was that what you're asking? What the?
What you're gonna tell us.
Oh yeah, I'm going to do it. Yeah. That's fine. All right. This is just you know, whatever perspective you want to have on this work. Is anything that works for you is fine. Otherwise, you can decouple, except perhaps the algebra. That may be something that is a more general interest. Let's see. Okay, so I will talk about beta functions. It will here in this talk just be about one loop, but of course I'm worried about higher loops. That's you know, outlook, and I've some you know, some ideas about them. Then I'm going to talk about algebras. You say that I could call them marginal algebras because they have the elements in the algebras are marginal couplings. The old reference is to Michel and Radicati. They found this a long time ago. These algebras, originally not to do with renormalization. In the common work, Michel later went on to discuss how it works in scalar theories without gauge interactions. We call these diamond products, the products in the algebras. They called it V products. I just kept the notation because, you know, we didn't know about the old use before we published the paper. And then I will tell you about the actual results for the models. So how do these models actually behave? All right. So this is the model. Gauge interactions, minimal coupling to scalars, and quartic couplings. I only care about the quartic couplings here. And notation, there are two different ways of writing this. I will. This is the more convenient way of writing in terms of matrices in the Lie algebra, and the A index is the index of the scalar, what scalar multiplet we're in. And these are supposed to be all the quartic interaction terms. Can be written down like this in this language. This form of the quartic interaction, the potential, is going to match with, you know, if we want to take results on beta functions from the literature, just sums over scalar fields with all the indices combined into a multi-index like this, and this would be the couplings. There are certain couplings here that correspond to the coefficients of these four invariant possible quartic interactions. Okay, so that's the model. Then, yeah, It's a simple X. This is a very basic talk, right? You see it's just the perturbation theory. There will be, for the one loop, beta functions of the scalar couplings. We already dealt with the one loop of the gauge coupling. For the scalar couplings, there will be contributions from repeated quartic interactions. There will be external leg corrections and these double exchanges, purely gauge particle induced. This term is the one we're going to be most interested in. These other terms are we can add on at the end. This is where the algebra sits. It's just, you can see that it's sort of a square in a sense of the coupling, right? So that can be thought of as an algebra in some way. So this sum we take to define a commutative product like this. It's just the definition. It can be written in terms of a more ordinary product, just product of matrices in sort of the two particle space like this. But you still have to sum over all the permutations that of course came from the permutations of all these diagrams. Oops, I'm just going to go like that. Now the product is distributive, and then this means that this product is also mathematically called an algebra. It's a bit curious because it's commutative, but in contrast to this, just the ordinary matrix product is not associative, right? So it's a bit unfamiliar. But that's just what life, that's what it is. Yes. Oops. It still appears. It still appears in the beta functions. It's obviously something that is of some physical interest, you know, written in a strange way, but we have it there. The last two lines here is more for higher loop considerations. It's you can skip it for the moment. So there's a lot of information in this algebra. You can extract a lot of things about the RG flow. There are also sort of experimental signs that there is more to it than just what I'll show you directly. I'll just indicate it. And I said they are known from, you know, the first paper on this kind of algebra is, in physics is this from 71. Michel went back in 81 and discussed this in the context of renormalization. So, you know, if it hasn't been used for that long time, maybe it's nothing to worry about, but I'll show you what I find, and I think it's intriguing. Any case, okay, in algebra, it's a linear space. You can choose a basis for it. The basis conveniently in our case would be to be the actual invariant couplings that I showed you, the four ones. In other theories, there would be different bases. So you can just decompose it like this in terms of the basis element. Beta functions will have a similar decomposition, and the components of the beta function can also be written. The full beta function equations can be written in terms of structure constants of this commutative, non-associative algebra. And they all can be extracted from this product, right? So now the task is to do this and then just get the beta functions. And then just look for the RG flow. Okay, this is a repeat of the notation. These are the objects of interest. You can notice that there are sort of two single trace operators and two double trace operators. They have will have different properties. We'll see that very clearly when we look at the algebra. All right, lots of now you can see here how efficient it is to write things in terms of polynomial. If instead you wanted to look at the tensor structure that contracts these scalar fields, they are here, right? For the four different invariant couplings, right? But these are interesting because we need them to do the contractions that enter in the beta function. They will also tell us about the algebra. All right. So here, for example, you have this single trace operator. It's a tree-level thing. I wrote it in terms of a kind of notation which is about similar to what's done in tensor models, connecting different. You have to keep track of all the indices and how they're contracted with each other in these different terms. And here they are. The blue lines are supposed to be the SUN indices in the adjoint, and the black lines are just the Kronecker deltas in the space, so the sort of a flavor space of these scalars, like this. If you then, this was starting from these, one of the invariants written down in terms of these diagrams. You can write all of them in terms of different topologies of these diagrams. You see clearly, the double trace nature of the last two by having just their disjoint parts to it, to the gauge structure. So then you just have to multiply these together. You can do that in some sort of diagrammatic bird track language or just using algebra. Eventually you get this summary, which is the algebra. Diamond products of these two elements give you this sum of elements. That's what an algebra is. You can check for yourself. If you don't do it in your head, you can work a little bit and you see that it's going to be non-associative in general. Curious, but that's it. I grouped the products in a certain manner here, but this is of course too complicated to digest. It's a bit simpler if you take the large n limit and define large n algebra elements, basis elements. Simplifies considerably. So what was done here is sort of a contraction of the algebra, similar to contractions of Lie algebras. I rescale coupling constants and tensor structures in this way, preserving the product like this. And then I make sure that the products, the structure constants do not diverge. Then I can get the reasonable, interesting contraction of the algebra. And to do that, I find that I have to do a scaling, which is precisely the ordinary, the 2 scaling of this kind of theories with single trace and double trace operators. So the algebra tells me about this. This is the way to do it. Interestingly, there are other possible large n limits This is the standard one. If I also allow m to grow, I get some sort of Veneziano-like limits. And the consistent ways of doing that, getting a finite structure constants, picks out particular Veneziano-like limits that are actually closely related to melonic limits that appear in tensor models, which I find intriguing. This is one of the sort of signs that this algebra summarizes something very important to us, for whatever that's worth. Now you can also read off interesting things about the renormalization group flow. Of course you can, because they summarize the renormalization to one loop order at least. A subalgebra is just a set of part of the algebra that closes. You can look at this three-dimensional subalgebra or that one-dimensional subalgebra. And say if you put all the other couplings to 0, you will, if those products close, you will stay in the subalgebra. So you will have closed renormalization group flows in these subsets of the space of couplings. That is, if it was not for the gauge coupling, which induces certain flows that can take you out of the subalgebra. But there is a more interesting structure, even more interesting than subalgebras, which is you combine the fact of being a subalgebra with something more. What would that be? Well, in algebras, there's a notion of an ideal, which is, it's also subalgebra, but has the added benefit of if you multiply an element of the ideal with any other element, it will stay in the ideal, the algebra ideal. If you do that, you can also define sort of a quotient algebra, and which is the sort of transfers to the subalgebra, and those, because of the fact that it's an ideal, you will find that those RG flows in the quotients, they will be independent of the couplings that are in the ideals. It's sort of a it's a semi-direct products in some way. So you simplify this set of couplings have a independent dynamical system in the renormalization group flow. And the others still have, the ones in the ideal also have some interesting properties. They're just subalgebras like the previous slide. But the fact that this is sort of isolating parts of the flow gives a hierarchic structure to the flow. It will give a hierarchic structure also to the set of fixed points, if you can find any. This is the whole set in the large n limit of the beta functions of these couplings mu that are scaled with the gauge coupling, right? Sometimes it's called fixed flows. The flows of these couplings, and if there are fixed points of these flows, they're fixed point of these RG equations, they are fixed flows. They will be roots of systems of second order polynomials. Here, I just have to admit that it's not very beautiful. This is the result, in a sense, a summary of the result, I would say. You can see the gauge coupling, how it behaves, depending on M, and the single trace couplings and the double trace couplings. Lots of different special cases. Fortunately, this hierarchical structure helps. And let's see, I kind of focus on something part of this picture. It turns out that there are no true fixed points, which sort of I hope to find fixed points that would be interesting. It would be defined conformal field theories, but in hindsight, you shouldn't have expected that. This would be the real fixed point. If here you would have if you had fixed points for the scalar couplings here, it would be a true fixed point for all couplings, a real conformal field theory. Doesn't happen. What happens to the flows of the scalar couplings as you increase M? Well, this is a hierarchic structure. Eventually here, what I've listed is, I thought, when do these theories make any sort of sense as in some limit, because you're already forced, if you're interested in fixed points, you're how should I say, if you're interested in these fixed points, you're forced by the structure to look at large M, and then the gauge coupling is IR free rather than UV free. So then I thought maybe it's interesting to look at what the possible structure is in the IR of these theories, and I listed cases where you have complete perturbative fixed points in the IR. There's no one that is completely stable, but there's one unstable directions for the green ones and two for the what we call cyan colored ones. For what that's worth, all of these have unstable directions. But you can, if you wish, sit on a fixed point. For the structure, you can plot what happens for various values of M. This is the single trace flows where M is large enough that you will actually have fixed points. There's one UV stable, one and one saddle. At those values, of the single trace couplings, you can look at the flows of the double trace couplings, and there's actually a set of fixed points there too. This is a coarse grain view. You can look closer at that, and you will find that these are actually, it's a long, narrow parallelogram, which if you look closely in this region, it separates into a saddle and IR stable fixed point. And the one below separates into UV stable and the saddle. This means that you could have in the IR theories that sit here and stay there, so they are perturbative. Oops. What did I do? That is, yeah, this is the example of what happens for when you don't have fixed point. You have flows like this that go from the, if you start, this is towards the UV and this in the IR. If you look at the IR, like that was sort of indicated the other diagrams. If you start out here for negative values of couplings, you usually have, you would expect to have, and you can follow that through, that you would have got Coleman-Weinberg radiative symmetry breaking. And then, of course, you would have to study again what happens if you wanted to. For us, I suppose it's time to close. And what to do next? here. There are a few exceptional cases that we haven't covered yet. The simple case of m equals 1 is not included actually because these 4 quartic couplings are linearly dependent in that case. So it's just a matter of checking it. I haven't done it. Then finite n, most of the things I showed you were for large n. And there could be interesting stuff at finite n, who knows. Higher loops, as was mentioned, obviously. But I do think it is interesting that what the algebra sort of indicates to us, that there are specific limits that have very nice properties. They are sort of singled out by the algebra, and we don't know yet all the things that this algebra can do in this system and in others. So that's where we are right now. Thank you. Some point what? No, that's I mean, they do diverge, but they don't actually bifurcate. It's if you go to higher resolution, it's sort of unique. Oh wait, I see. Let me think what you mean. Well, it takes that direction. Yeah. I suppose you can, if you take it as a flow from minus infinity plus infinity, it will go either on one side or not. There will be lines in between. It's continuous in a way. Yeah. No, I wouldn't call it exactly bifurcation, but it's similar. Yes. Yeah. Yeah. I don't. Yeah, I mean, you do scale in a different way. So it is precisely as you say. Well, that's what you would think, but you could scale away that in principle. I'm not saying this is going to happen, but you can scale that those terms in the beta functions to 0. It could happen, and that would be super interesting, of course. But it doesn't look like it happens in a simple way. It could still happen in a complicated way, but we are exploring that. Yeah, of course we are. Yeah. Yeah, that was the starting point. I mean, I'm actually not that interested in that any longer. It also looks like I mean, who knows? But yeah, I mean, there are. If you take a Venetiano-like limit, large M, it is like a large dimension limit of D-branes, and you could think about large dimension limits of gravity and things like that. But and if you want that is related to some sort of string theory or not, I still, yeah, I mean, the higher loop question for M equals 26 is of course important to check. It doesn't look promising, but we're also checking that.